Hello, in this lecture we'll find out the length of line segment X. In the drawing we have two quarter circles. Those two quarter circles start each other here at point B. In addition, we know that line segment AB equals to 1 unit in its length, and line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC, is equal to X. So first of all, because of the fact that this is a quarter circle, it means that PA, line segment PA equals to line segment AB. They are both the radii of this quarter circle, therefore they are equal to each other. And we know that AB equals to 1, therefore PA must be also equal to 1. Likewise, we know that QCB is a quarter circle. In this quarter circle QCB, QC equals to CB. They are both the radii of this quarter circle, therefore they are equal to each other. And it is given as an equation that BC equals to X, therefore QC must be also equal to X. In the next step, we will join points P and B together by a straight line. And we'll also join points Q and B together by a straight line. So we have here the right triangle PAB. I'll copy the right triangle PAB in a new page, and we'll implement the Pythagoras theorem on this right triangle PAB. Where PT is the relation for Pythagoras theorem. Firstly, this is the right triangle PAB that I covered from the original drawing. In this right triangle PAB, according to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1 square, that is 1. So in total PB square equals to 1 plus 1, that is 2. So PB square equals to 2. We take a root out of this equation, and finally we get that PB equals to the square root of 2. Okay, the hypotenuse PB equals to the square root of 2 units in its length. So we can write down here that PB equals to the square root of 2 units in its length. In this right triangle PAB, PA equals to PA equals to AB. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle PAB. So in the right triangle PAB, which angles we have? In the right triangle PAB, we have this angle, this is alpha, this angle is alpha, and this angle is 90 degrees. So alpha plus alpha is 2 alpha. 2 alpha plus 90 degrees, it must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. We divide this equation by 2 and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So this is again alpha is equal to 45 degrees in its size. And this is also angle alpha is equal to 45 degrees. If we repeat on the same process on the right triangle QCB, we arrive to the conclusion that those two angles, each of them is equal to 45 degrees. In the next step, I will copy the right triangle QCB in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle QCB. By PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QCB that they copied from the original drawing. In this right triangle, triangle QCB, according to the Pythagoras theorem, QB squared equals to QC squared plus BC squared. Repeat again. QB squared equals to QC squared plus BC squared. So QB squared, that is the square of the hypotenuse, equals to QC squared. QC is x, therefore QC squared is x squared, plus BC squared. BC is x, therefore BC squared is x squared. So in conclusion, we found out that QB squared equals to x squared plus x squared, that is 2x squared. QB squared equals to 2x squared. We take out all of this equation and finally we get that QB equals to the square root of 2x squared. That is to say, QB equals to the square root of 2 and the square root of x squared is x. So in total, QB equals to the square root of 2 times x. Here the hypotenuse QB of the right triangle QCB, it is equals to square root of 2 times x units in its length. In the next step, I will present to you rule number 3 and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. In the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule, rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle that is beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. So we can actually implement rule number 3 in our drawing. Why? Because in our drawing, if we focus on the upper side of this straight line AC at point B, here the sum of the angles must be equal to 180 degrees. So I copy the straight line in AB with point B in a new page and we implement rule number 3 on this straight line AC. So actually, this is the straight line AC that I copied from the original drawing. We focus on the upper side of the straight line AC at point B. Which angles we have at the upper side of AC at point B? We have this angle that is 45 degrees, plus the missing angle that we will define as X, plus this angle that is 45 degrees. In total, the sum of those three angles must be equal to 180 degrees. So 45 plus 45 is 90, so 90 degrees plus X equals to 180 degrees. We subtract 90 degrees from this equation, and finally we get that X equals to 180 degrees minus 90 degrees, it is 90 degrees. So the missing angle here is a right angle, it is equals to 90 degrees. So to write down here, in the original drawing, this is the missing angle, X that is equal to 90 degrees, and its size it is a right angle. And therefore triangle QBP is a right triangle. So I copy the right triangle QBP in a new page, and we block this right triangle QBP by a circle. We have the rule that any triangle can be blocked by a circle, and especially the right triangle QBP. So actually, this is the right triangle PBQ that I copied from the original drawing. And I block this right triangle PBQ by this circle. So in the drawing, we have peripheral angle PBQ. This peripheral angle PBQ is equals to 90 degrees in its size. And we have rule number 5 that relates to a peripheral angle that is equals to 90 degrees. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. In the drawing we have a circle, inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size. Therefore, this peripheral angle MAN must rest on the diameter of the circle, that is to say MN is the diameter of the circle. And indeed, MN is the diameter of the circle. Why? Because chord MN passes through point O, that is the center of the circle, and we have the rule that any chord that passes through the center of the circle must be the diameter of the circle. In conclusion, we can say that because of the fact that this peripheral angle MAN equals to 90 degrees, therefore it rests on the diameter of the circle. MN is the diameter of the circle. Okay, you can implement rule number 5 in our drawing. Why? Because in our drawing we have this peripheral angle PBQ is equal to 90 degrees in its size, therefore this peripheral angle rests on the diameter of the circle. That is to say, PQ is the diameter of the circle. PQ is the diameter of the circle, and if we define the radius of this circle as r, then the diameter PQ must be equal to 2r. Okay. In the next step, so we have PQ, then I copied side PQ of the right triangle PBQ here. So I'll copy point S that is located on QP to our new drawing here. So this is point S that I copied from the original drawing. Exactly, we put it on the same location as it is here on the diameter QP. Okay, so I copied point S from the original drawing to our new drawing here. It is given us the equation that PS equals to SQ. So if PS is X, then SQ must be also equal to X because they are equal to each other. So the length of PQ in total it is equals to PS plus SQ. That is to say PQ equals to PS that is X plus SQ that is also X. So in total PQ equals to X plus X, that is 2X. So PQ equals to 2x from one side, but from the other side, we already found out that PQ equals to 2r, it is the diameter of the circle. And from those two equations, PQ equals to 2x and PQ equals to r, we will derive that 2x equals to 2r. Here we'll divide this equation by 2 and finally we will get that x equals to r. So here we have PS is x and x equals to r. We have here SQ is also x and x equals to r. So PS equals to r. PS equals to r. So we can write here that PS equals to r. It is the radius of this circle. And SQ is also equals to r. So we can write here that SQ is also equals to r. So QS is r and PS is also r. So those two radii of this circle touch each other at point S. Therefore point S is the center of the circle. So I write it down. Point S is the center of the circle. Because at the center of the circle, all the radii touch each other. In the next step, we'll join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of this circle that is equal to 1. In conclusion, we found out that PS equals to SQ equals to SB, all those three line segments are equal to each other because of the fact that each of them is the radius of this circle, therefore they are equal to each other. So here we join points S and B together by a straight line. SB is the radius of the previous circle, that is equal to R. And here also PS equals to SB equals to SQ. They are all the radii of the previous circle, therefore they are equal to each other. So in the next step, I will do a construction. That is to say, I'll copy this quarter circle to a new page and we will complete this quarter circle to a circle. Repeat again, I copied this quarter circle to a new page here. This angle equals to 90 degrees, and we already found out that QS equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. So in the next step, I will present to you a new rule and we will implement the new rule in our drawing. But first of all, I'll complete this quarter circle to a circle. So we completed the quarter circle to a circle. In the next step, I present to you a new rule and we will implement the new rule in our drawing. According to the new rule, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle, inside this circle we have peripheral angle ASB, this is peripheral angle ASB, and peripheral angle ASB equals to theta in its size, and this peripheral angle ASB is subtended on this arc AB. In addition we have another angle, this is the central angle AOB, the central angle AOB is subtended on the same arc AB. In conclusion, we have here a central angle that is subtended on the same arc as the peripheral angle. The central angle and the peripheral angle, they are both subtended on the same arc AB. And therefore, according to this rule number 13, the central angle AOB must be twice as large as the peripheral angle ACB that is subtended on the same arc AB. Okay, you can actually implement rule number 13 in our drawing. Why? Because in our drawing we have peripheral angle BSQ this peripheral angle BSQ is subtended on RQB. And we also have the center angle QCB, this center angle QCB. This is actually the center angle QCB. This center angle QCB is subtended on the same arc, RQB. And therefore, according to rule number 13, this center angle QCB must be twice as large as the peripheral angle BSQ that is subtended on the same arc, RQB. So we have to find out the size of this center angle QCB. In order to find out the size of this center angle QCB, I present to you rule number 6, and we will implement rule number 6 in our drawing. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. In the drawing, we have this point A, and according to this rule number 6, the sum of the angles around this point A equals to 360 degrees. In order to prove that rule number 6 is true, here I drew this straight line that is passes for point A. So here, according to rule number 3, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees. Likewise, according to the same rule number 3, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A and the sum of the angles in the lower side of this straight line at point A will be equal to 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule number 6, that says that the sum of the angles around point A equals to 360 degrees. We can actually implement rule number 6 in our drawing. Why? Because in our drawing, we have, if we focus at this point C, we know that the sum of the angles around point C, according to rule number 6, must be equal to 360 degrees. So which angles we have around point C? We have this angle, this is a right angle, this is equal to 90 degrees. So 90 degrees plus the missing angle, in total, they must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees equals to 360 degrees, exactly according to rule number 6, that says that the sum of the angles around point C must be equal to 360 degrees. So the center angle QCB, this is the center angle QCB, that is equal to 270 degrees. Therefore, the peripheral angle BSQ that is subtended on the same arc BQ must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. Okay. So we focus on triangle BSQ. On this triangle BSQ, we already found out that BS equals to SQ. Those two sides are both the radii of the previous circle, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we know that the sum of the angles in any triangle, and especially in triangle BSQ, must be equal to 180 degrees. So which angles we have inside the triangle BSQ? We have alpha plus alpha, that is 2 alpha plus 135 degrees. In total, the sum of those three angles must be equal to 180 degrees. So 2 alpha plus 135 degrees equals to 180 degrees. According to the rule that I mentioned, I relate to the associated triangle, triangle BSQ. The sum of the angles in the associated triangle, triangle BSQ must be equal to 180 degrees. So here we subtract 135 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. So 2 alpha equals to 45 degrees. We divide this equation by 2, and finally we get that alpha equals to 45 over 2 degrees. So this is angle alpha that is equals to 45 over 2 degrees, and this is also angle alpha that is equals to 45 over 2 degrees. Okay, so in the next step I will copy the right triangle, triangle PBQ in a new page, and we will analyze this triangle, triangle PBQ. This is angle alpha that is equal to 45 over 2 degrees. Actually, this is the right triangle, triangle PBQ that I copied from the original drawing. Side PB equals to the square root of 2 units in its length. And this side QB equals to the square root of 2 times x units. So in this, and we already found out that this is angle alpha that is equals to 45 over 2 degrees. So in this right triangle, triangle PBQ, tangents 45 over 2 degrees equals to PB over QB. Tangents 45 over 2 degrees equals to PB over QB. So tangents 45 over 2 degrees equals to PB. PB is square root of 2 over QB. QB is square root of 2 times x. So here we have square root of 2 in the numerator and square root of 2 in the denominator. So square root of 2 will get cancelled, and you're left only with 1 over x. In conclusion, we found out that according to equation number 1, this will be equation number 1. Tangents 45 over 2 degrees equals to 1 over x. This is equation number 1. And we also have the trigonometric identity that states that tangents to theta equals to 2 times tangents theta over 1 minus tangents square theta. We will define angle 45 over 2 degrees, is actually 22.5 degrees, is theta. So theta equals to 45 over 2 degrees according to our definition. So if theta equals to 45 over 2 degrees, it means that 2 theta must be equal to 45 degrees. In the next step, we will substitute 2 theta in this trigonometric identity by 45 degrees, and we substitute theta in this trigonometric identity by 45 over 2 degrees. And we'll get that this will be equation number 2. According to equation number 2, we have here tangents 2 theta, and 2 theta according to our definition is 45 degrees, and it is equals to 2 times tangents theta, and theta according to our definition is 45 over 2 degrees. So in total, in the numerator of this side of the equation, we have 2 times 45 over 2 degrees over 1 minus tangents square theta, and theta according to our definition is 45 over 2 degrees. In conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. So here tangents 45 degrees is 1, that is equals to, here we will define tangents 45 over 2 degrees as t, tangents 45 over 2 degrees equals to t according to our definition. And we substitute tangents 45 over 2 degrees in this equation, equation number 2, by t. And we get that tangents 45 degrees is 1, so 1 equals to 2 times tangents 45 over 2 degrees, that is t. So we substitute tangents 45 over 2 degrees by t. So in total, in the numerator, we will have 2t over 1 minus tangent square 45 over 2 degrees. If tangent 45 over 2 degrees is t, then tangent square of 45 over 2 degrees will be equal to t square. So in total, in the denominator, we have 1 minus t square. In conclusion, we found out that according to equation number 2, 1 equals to 2t over 1 minus t square. Here we will multiply this equation, equation number 2, by 1 minus t square. And we get that according to this equation, equation number 2, 1 minus t square equals to 2t. Here we relate to this equation, equation number 2t square. And we get that according to equation number 2, t square plus 2t equals to 1. Here we subtract 1 from this equation, equation number 2, and finally we get that t squared plus 2t minus 1 equals to 0. So this is a quadratic equation. T squared plus 2t minus 1 equals to 0 is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Okay. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. Okay. So this is the data that we have for our specific quadratic equation. In the next step, we will put this data inside this general formula for x, and we'll find out the value of the values of t because x equals to 3. So because x equals to t. So x equals to 3, so we substitute x by t, and we get that t equals to minus b. B is 2, so minus b is minus 2, plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4. Minus 4 times a is 1, times c is minus 1, all divided by 2 times a. A is 1, so it is 2 times 1. Okay. So here actually found out that t equals to minus t plus minus square root of 4 minus 4 times minus 1 over 2. So t equals to minus 2 plus minus square root of minus 4 times minus 1 is plus 4, and 4 plus 4 is 8. So in total inside the root we have only 8 divided by 2. So t equals to minus 2 plus minus square root of 8. 8 is 4 times 2, so we substitute 8 by 4 times 2 over 2. So in conclusion, we found out actually that t equals to minus 2 plus minus the square root of 4 is 2. Inside the root we left only with 2, all divided by 2. Repeat again, we actually found out that t equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over 2 is minus 1, plus minus, and 2 over 2 is 1, so in total this expression equals to the square root of 2. In conclusion, we found out actually that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. This is the first solution for t. And the second solution for t is that t equals to minus 1 plus square root of 2. Okay. According to the first solution for t, t equals to minus 1 minus square root of 2. That is to say, minus 1 minus square root of 2 is a negative number. That is to say, t is a negative number. But according to our definition, t equals to tangents 45 over 2 degrees. That is a positive number. That is to say, according to our definition, t must be a positive number. And a positive number can never be equal to a negative number. And therefore, we got to a contradiction. Therefore, we cancel this solution. This solution is incorrect. So we left only with the second solution that is possible for t. That t equals to minus 2 plus square root of 2. And according to our definition, t equals to tangents 45 over 2 degrees. And t, according to the second solution, equals to the square root of 2 minus 1. So this is actually equation number 2 that states that tangents 45 over 2 degrees equals to square root of 2 minus 1. This is according to equation number 2. While according to equation number 1, we have already found out that tangent 45 over 2 degrees equals to 1 over x. So we write it down. According to equation number 1, we have already found out that tangent 45 over 2 degrees equals to 1 over x. So here we have two equations for the value of tangent 45 over 2 degrees. Therefore, we create equation number 3 that states according to equation number 3, tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Okay, again, according to equation number 3, tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Tangents 45 over 2 degrees according to equation number 1 is equals to 1 over x, and it must be equal to tangents 45 degrees according to equation number 2, that is actually equals to the square root of 2 minus 1. In conclusion, we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation number 3 by x, and we get that according to equation number 3, x equals to the square root of 2. Here 1. We multiply this equation by x, and we get that here 1 over x times x is 1. So 1 equals to the square root of 2 minus 1 times x. Here we divide this equation number 3 by x, and finally we will get that x equals to 1 over square root of 2 minus 1. Okay, so I actually found out that x equals to 1 over square root of 2 minus 1. X equals to 1 over square root of 2 minus 1. So here we will multiply this side of the equation by square root of 2 plus 1, and then we will divide it by square root of 2 plus 1. We will multiply it by square root of 2 plus 1, and then we will divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is of course 1. And it is allowable to multiply anything by 1, we change nothing. Therefore, this operation is allowable. So actually found out that x equals to, in the numerator we have square root of 2 plus 1 over square root of 2 plus 1 times square root of 2 minus 1. This expression, square root of 2 plus 1 times square root of 2 minus 1 is equals to, according to the algebraic identity, that a plus b times a minus b equals to a squared minus b squared. We will get that square root of 2. So x equals to the square root of 2 plus 1 over this expression according to this trigonometric identity will be equals to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So x equals to the square root of 2 plus 1 over 1. Square root of 2 plus 1 over 1 is square root of 2 plus 1. Okay? In conclusion, found out actually that x equals to either square root of 2 plus 1 units in its length, or in terms of numbers, x equals to 2.414 units. And that is the answer to our question. I repeat again, we actually found out that this line segment BC is equal to x. It is equals to either square root of 2 plus 1 units in itself, or line segment BC is equal to x. It is equals to 2.414 units. Okay, so in the next step I will summarize the lecture. In this lecture, we found out the length of this line segment BC is equal to x. So in the drawing, we have those two quarter circles. Those two quarter circles touch each other here at point B. In addition, we know that AB equals to 1 unit in its length, line segment AB equals to 1 unit in its length, and also QS equals to SP. And our mission is to find out the length of this line segment BC that is equal to x. So this is a quarter circle, and therefore this angle will be equal to 90 degrees. Likewise, this is a quarter circle, therefore this angle will be always equal to 90 degrees. In addition, we know that PA and AB, they are both the radii of this quarter circle, therefore they are equal to each other. But AB equals to 1 according to what is given as the question. Therefore, PA will be also equal to 1. Likewise, BC and QC are the radii of this quarter circle, and therefore they are equal to each other. And because of the fact that BC equals to x, then QC must be also equal to x. Then we join points P and B together by straight line, and join points Q and B together by straight line. By joining points P and B, we created the right angle PAB. So I copied the right angle PAB in Olympiad, and we implemented the Pythagoras theorem in this right angle triangle PAB. In the right angle PAB, according to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square equals to PA square, PA is 1, therefore PA square is 1 square, that is 1, plus AB square, AB is 1, therefore AB square is 1. So in total PB square is 1 plus 1, that is 2. So PB square equals to 2. Then we took a root out of this equation and finally found out that PB equals to the square root of 2 units. Here, therefore this importance PB is square root of 2 units. Then we continue to focus on the right angle PAB. On this right angle PAB, PA equals to AB, side PA equals to side AB, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we will have those two angles that also must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we also know that the sum of the angles in any triangle must be equal to 180 degrees. So which angles we have in the right angle PAB? We have alpha plus alpha, that is 2 alpha plus 90 degrees. In total, it must be equal to 180 degrees. Repeat again, in the right angle PAB, 2 alpha plus 90 degrees must be equal to 180 degrees. We subtract the 90 degrees from this equation and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equal to 45 degrees, and this is angle alpha that is equal to 45 degrees in its size. Then I copied the right angle QBC in the new page and represented the Pythagoras theorem on this right angle, triangle QBC. This is the right angle QBC that I copied from the original domain. In this right angle QBC, QB square equals to QB square equals to QC square plus BC square. Repeat again, in the right angle QBC, QB square equals to QC square plus BC square. So QB square equals to QC square. QC is x, therefore QC square is x square, plus BC square. BC is x, therefore BC square is x square. So in total, QB square equals to x plus x, that is x square plus x square, that is 2x square. So QB square equals to 2x square. We took out of this equation and finally found out that QB equals to the square root of 2 times x square. That is to say, QB equals to the square root of 2, and the square root of x square is x. So in total, QB equals to the square root of 2 times x. Here, the hypotenuse QB of the right angle QBC equals to the square root of 2 times x units in its length. Then I presented to you rule number 3, we implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the domain we have the straight line AB. If we focus on the upper side of this straight line AB at point Q, we have the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. We can actually implement rule number 3 in our drawing. Why? Because in our drawing, if we focus on the straight line AB at point B, if we focus on the straight line AC, this is the straight line AC at point B, the sum of the angles in the upper side of AC at point B must be equal to 180 degrees according to rule number 3. So I copied the straight line AC at point B in a new page and we implemented rule number 3 in this straight line AC. So actually this is the straight line AC that I copied from the original drawing. This is point B. Here the sum of the angles on the upper side of AC at point B must be equal to 180 degrees. So which angles we have at the upper side of AC at point B? We have this angle that is 45 degrees, plus the missing angle that we defined as x, plus this angle that is 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus x equals to 180 degrees. Here we subtract the 90 degrees from this equation and finally found out that the missing angle, angle x equals to 90 degrees. So actually, this is the missing angle x is equal to 90 degrees in its size. So if this angle equals to 90 degrees, it means that triangle QBP is a right angle. Then I copied the right angle QBP in a new page and I broke this right angle QBP by a circle. We have the rule that any triangle can be blocked by a circle. So this is the right angle QBB that I copied from the original domain, and then I block this right angle by this circle. So in the domain we have peripheral angle PBQ that is equal to 90 degrees, and we have rule number 5 that relates to any peripheral angle that is equal to 90 degrees in its size. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. In the domain we have a circle, inside the circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in size. Therefore, this peripheral angle MAN rests on the diameter of the circle. That is to say, MN is the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle PBQ that is equal to 90 degrees in size. Therefore, this peripheral angle PBQ rests on the diameter of the circle. That is to say, PQ is the diameter of the circle. So if we define the radius of this circle as R, then the diameter PQ must be equal to 2R. That is from one side, but from the other side, it is given us the equation that PS equals to SQ. So if PS is X, then SQ must be also equal to x because they are equal to each other. So PQ in total equals to PS, that is x, plus SQ, this is also x. So in total, PQ equals to x plus x, that is 2x. So PQ from one side equals to 2x. From the other side, we just right now found out that PQ is the diameter of the circle, that is to say it is equals to 2r. And from those two equations, PQ equals to 2x and PQ equals to 2r, we will derive that 2x equals to 2r. Here we divided this equation by 2 and finally found out that x equals to r. Okay, x equals to r. So we can write here that PS, that is x, equals to r, and SQ, that is also x, equals to r. Then I copied point S from the original drawing to our new drawing. This is actually point S that I copied from the original drawing here to our new drawing. PQ is the diameter of the circle. Okay, we've already copied PQ and we blocked the triangle PQB by this circle. And now I copied point S that is located on the diameter PQ to our new drawing here. This is point S that I got from the original drawing. So we have already found out that PS equals to R and SQ also equals to R. So those two radii of this circle touch each other at point S. Therefore point S is the center of the circle. Point S is the center of the circle. Then we join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle that is equal to R. In conclusion, we found out that PS equals to SQ equals to SB. All those three line segments are equal to each other. Why? Because all of them, each of them is the radius of the circle, and therefore they are equal to each other. And here also in the original drawing, we join points S and B together by a straight line. SB is the radius of the previous circle that is equal to R. In conclusion, found out that SB equals to SQ and it is equals to SP. They are all the radii of the previous circle, therefore they are equal to each other. In the next step, I copied this quarter circle to a new page, and in the next step I completed this quarter circle to a circle. So actually this is the quarter circle that I copied from the original drawing, and then I completed this quarter circle to a circle. We have already found out that SQ equals to SB. Both of those two sides are the radii of the previous circle, therefore they are equal to each other. This angle equals to 90 degrees. I copied it from the original drawing. And then I presented to you rule number 13, and you implemented rule number 13 in our drawing. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. In the drawing we have this circle, inside this circle we have this peripheral angle ACB that is equal to theta in its size, and this peripheral angle ACB is subtended on RKB. In addition, we have here the central angle AOB. This is the central angle AOB that is subtended on the same arc RKB. So, in conclusion, the drawing we have a peripheral angle and a central angle. Both of them are subtended on the same arc AB. Therefore, according to this rule, rule number 13, the central angle AOB must be twice as large as the peripheral angle ACB. And the peripheral angle ACB equals to theta, therefore the central angle AOB must be equal to 2 theta. We can actually implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle BSQ. This peripheral angle BSQ is subtended on arc QB, And we have also the center angle QCB. This is the center angle QCB that is subtended on the same arc QB. Therefore, according to rule number 13, the center angle QCB must be twice as large as this peripheral angle QSB that is subtended on the same arc QB. Okay, so we have to find out the size of the center angle QCB, the size of this angle. In order to find out the size of this angle, I presented to you rule number 6, and we implemented rule number 6 in our drawing. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around point A equals to 360 degrees. In order to prove that this rule is true, I drew this straight line that passes point A. Here we can use rule number 3. According to rule number 3, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees. Likewise, the sum of the angles on the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A plus the sum of the angles in the lower side of this straight line at point A must be equal in total to 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule, that the sum of the angles around point A must be equal to 360 degrees. We can implement rule number 6 in our drawing. Why? Because in our drawing, if we focus at this point C, here, according to rule number 6, the sum of the angles around this point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is right angle that is equal to 90 degrees, plus this missing angle, plus this missing angle. In total, the sum of those two angles must be equal to 360 degrees according to rule number 6. Therefore, this missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is 360 degrees, exactly according to rule number 6, that says that the sum of the angles around point C must be equal to 360 degrees. Therefore, this missing angle equals to 270 degrees. That is to say, the center angle QCB equals to 270 degrees. Therefore, the peripheral angle BSQ that is subtended on the same arc QB as the peripheral angle QCB must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So this angle equals to 135 degrees. And so in the next step we focused on the associated triangle SQB. Here SQ equals to SB. Therefore, it is an associated triangle. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we also note that the sum of the angles in any triangle, and especially in triangle BSQ, equals to 180 degrees. So which angles we have inside the associated triangle BSQ? We have alpha plus alpha, that is 2 alpha, plus 135 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. Here we subtracted 135 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. So 2 alpha equals to 45 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 over 2 degrees. So this is angle alpha that is equals to 45 over 2 degrees, and this is also angle alpha that is equals to 45 over 2 degrees. Okay, then I copied the right triangle PBQ in a new page, and we analyze this right triangle PBQ. This is the right triangle PBQ that I copied from the original drawing. Side PB equals to the square root of 2 units, side BQ equals to the square root of 2 times x units, and this is angle alpha that is 45 over 2 degrees. So in this right triangle PBQ times 45 over 2 degrees equals to PB over BQ. times 45 over 2 degrees equals to PB over BQ. That is to say, it is equals to PB, that is square root of 2 units, over BQ or QB, that is square root of 2 times x. So here we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 gets cancelled and we left only with 1 over x. That is to say, we found out that according to equation number 1, times 45 over 2 degrees equals to 1 over x. I repeat again, times 45 over 2 degrees equals to 1 over x. This is according to equation number 1. Well, according to equation and here, so according to equation number 1, times 45 over 2 degrees equals to 1 over x. And we have the trigonometric identity that states that tangent 2 theta equals to 2 tangent theta over 1 minus tangent square theta. Then we defined theta as 45 over 2 degrees. So if theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. In the next step, we substitute 2 theta by 45 degrees because 2 theta equals to 45 degrees according to our definition. And we substitute theta by 45 over 2 degrees in this trigonometric identity. And found out that according to this trigonometric identity, here we have tangents 2 theta. And 2 theta is 45 degrees. So it is tangents 45 degrees. That is equal to 2 times tangents theta. And theta is 45 over 2 degrees. So this expression in total equals to 2 times tangents 45 over 2 degrees. Repeat again, actually found out that tangents 45 degrees equals to 2 times tangents 45 degrees over 2 times 45 over 2 degrees over, in the denominator we have 1 minus tangent square theta. So it is actually 1 minus tangent square theta, and theta is 45 over 2 degrees. So in conclusion, according to equation number 2, we found out that tangent 45 degrees equals to 2 times 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Tangent 45 degrees is 1, and it is equals to, here we defined tangent 45 degrees over we define tangent 45 over 2 degrees as t. Repeat again, tangent 45 over 2 degrees equals to t according to our definition. And here we substitute tangent 45 over 2 degrees by t. So in total, in the numerator, we will have 2t over 1 minus tangent square 45 over 2 degrees. So if tangent 45 over 2 degrees equals to t, it means that tangent square 45 over 2 degrees will be equal to t squared. So in total, in the denominator we have 1 minus t squared. In conclusion, found out that according to equation number 2, 1 equals to 2t over 1 minus t squared. Here we multiply this equation number 2 by 1 minus t squared, and found out that according to equation number 2, 1 minus t squared equals to 2t. So here we added to this equation number 2 t squared, and finally found out that t squared plus 2t equals to 1. Here we subtracted from this equation number 2 1, and finally found out that according to equation number 2, t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. Repeat again. X equals to t equals to 1, b equals to 2, and c equals to 1. So we put the data inside the formula for x and found out the value the value of the values of t because x equals to t. So we substitute x by t. So t equals to minus b. B is 2, so minus b is minus 2. Plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4. Minus 4 times a is 1, times c is minus 1. Over 2 times a is 1, so it is 2 times 1. So here we have t equals to minus 3 plus minus. Inside the root we have minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8, divided by 2. So t equals to minus 2 plus minus 8 is 4 times 2 over 2. And the square root of 4 is 2, so inside the root we left only with 2. So in conclusion, we found out that t equals to minus 2 plus minus 2 times square root of 2. So here we have two solutions, but here we divided the equation by 2. So t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1, so in total this expression equals to the square root of 2. In conclusion, we found out that t equals to minus 2 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t is that t equals to minus 1 plus square root of 2. So here t equals to, according to the first solution, t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2 is a negative number, but according to our definition, t equals to times 45 over 2 degrees, that is a positive number. So a negative number can never be equal to a positive number, so we cancel this solution, and we're left only with the second solution that is possible for t, that t equals to minus 1 plus square root of 2. And according to our definition, t equals to times 45 over 2 degrees. That is equals to t, that is minus, that is equals to t, that t is square root of 2 minus 1. So we have here equation number 2. According to equation number 2, times 45 over 2 degrees equals to the square root of 2 minus 1. Well, according to equation number 1, we already found out that times 45 over 2 degrees, times 45 over 2 degrees equals to 1 over x. So we have here two equations for times 45 over 2 degrees. Therefore, we created equation number 3 that states the times 45 over 2 degrees according to equation number 1 must be equal to times 45 over 2 degrees according to equation number 2. Times 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to times 45 over 2 degrees according to equation number 2. That is actually square root of 2 minus 1. So in conclusion, we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation by x and found out that 1 equals to square root of 2 minus 1 times x. Here we divided this equation number 3, by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. So x equals to 1 minus square root of 2 minus 1. In the next step, we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1. So here, in the numerator we have square root of 2 plus 1. In the denominator we have square root of 2 plus 1 times square root of 2 minus 1. Square root of 2 plus 1 times square root of 2 minus 1 will be equal to, according to this algebraic identity, that a plus b times a minus b equals to a squared minus b squared. According to this algebraic identity, we will get that the value of this expression will be equal to the square root of 2 squared, that is 2, minus the square root of 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So in the denominator, we left only with 1. So in conclusion, found out that x equals to square root of 2 plus 1 over 1, that is square root of 2 plus 1. In conclusion, found out that x equals to either square root of 2 plus 1 units in its length, or in terms of numbers, x equals to 2.414 units. I repeat again, we actually found out that this line segment BC that is equal to x will be equal to either square root of 2 plus 1 units in its length, or BC that is equal to x is equals, in terms of numbers, it is equals to 2.414 units. Okay, thank you very much.